this is a lecture for the independent t-test and the Mann-Whitney u-test. These two tests are a type of inferential statistical analysis. They fall under the umbrella of inferential statistics. One is a non-parametric, which is a Mann-Whitney, and the other is a parametric, which is the t-test. I'll talk a little bit about what constitutes the difference between parametric and non-parametric on the following slides. But essentially what we're looking at here is focus on the term independent t-test. There's also a dependent t-test, but in this instance we're learning about the independent t-test, and essentially we're looking at the differences, the statistical differences that are observed between two groups who are unrelated. So there's a couple different variations here that can determine what constitutes two groups, unrelated groups. So for example, if you look under the first bullet point, intervention group and a non-matched comparison group, essentially what that is if you have a two-group design, post-test only, and one group receives the intervention and the other group is the control group who doesn't receive the intervention. So here we have two groups, okay, unrelated, and we could use a t-test to determine the differences based on whatever outcome we're looking at. Another way to distinguish between two groups is use a grouping variable that's dichotomous, for example, like males and females. And to be more specific, we can look at other ways of distinguishing groups or splitting them up, groups with or without a medical condition, and that would be a dichotomous variable again. So you need that dichotomy there to separate the two groups. Okay. Testing the mean differences is for the independent test, t-test, and if we're looking at the median differences, we would use the Mann-Whitney u-test. So I included this. There's a little bit of a description in the text, and I always like to go to the statistics glossary. Remember, like I always said, that it's important to understand terminology before gaining a greater conceptual understanding of what's being taught. So looking at the difference between a parametric and a non-parametric, non-parametric tests are used in place of their parametric counterparts when certain assumptions about the underlying population are questionable. So if you remember in the previous discussions, we talked about the assumption of normality, the central limit theorem, and all those good theories related to the issues of probability testing and probability theory. So when comparing two independent samples, the Mann-Whitney test does not assume the difference between the samples. The difference between the sample is normally distributed, whereas a parametric counterpart, for example, like the t-test, we do have to follow that assumption that we are utilizing data from a normally distributed population. And if you use a t-test on data that is not normally distributed, then you're violating that assumption, and to what extent depends on whether or not you may end up with that type 1, type 2 error, okay? So it's always important to do preliminary analysis before you run these one of these inferential statistics, okay? Now, parametric tests may and often are more powerful in detecting population differences when certain assumptions are not satisfied. These certain assumption they're just talking about right here is the assumption of normality. So we always assume that the population is normally distributed. So how do you really ensure that your data is collected from a normal population? Well, you get a large enough sample size. Remember the law of large numbers. Or you use a nice methodological approach where you use random selection from a population. Things of that nature. Could talk a little bit about that more. So here, I just laid it out for you. So when we're choosing between the independent t-test and the main Whitney U, so if we're going to do the t-test, we have to understand that we have to have that dichotomous grouping variable. Remember, one group receives intervention, the other group doesn't, or we can split the groups and using some kind of statistical procedure like separating males from females, or those who have been diagnosed with this medical condition compared to those who haven't, whatever it may be. The second assumption is one of the more important ones. Data to measure the outcome variable is normally distributed. It can be a ratio or interval, and oftentimes you see the term continuous in place of this, so not to be confused with that terminology. And the other assumption is of independence. So you always want to assume that the data collected is from an independent random sample. And oftentimes this is not achieved, but it doesn't mean just because it's not necessarily achieved that you have to use some type of alternate analysis. You just have to interpret your outcomes with caution, knowing that that assumption were violated. So let's say for the main Whitney U, our non-parametric test, we still have to have our dichotomous grouping variable, but the data doesn't have to necessarily be distributed, normally distributed, and it has to be at least ordinal. We still have our independence assumption, and in this case, you need a total sample size roughly of about 8. And sample size and whatnot can also oftentimes be disputed. Okay, so going back to our grouping variable, it's nominal and dichotomous. Remember what a nominal measurement scale is. It's also that qualitative is, you can't rank it. There's no absolute zero. It's not interval. Okay. It also defines the two groups that are being compared. Sometimes the independent variable, such as gender or immunization status, or whether or not one received the intervention and the other did not. In the case where you have that post-test design, that I was talking about, that two-group post-test design, one group receives the intervention, the other doesn't. With the group that receives the treatment is actually the independent variable. Another group who doesn't is a control group, okay? Characteristic of interest variable, this can get a little bit confusing. You may have never even heard of this. Well, what's a characteristic of interest? It's more or less the outcome variable. And in most cases, it's that dependent variable. It should be at least interval or ratio or continuous. That's more of a catch-all term or phrase that you see in statistics. It's typically the dependent variable. And again, like I said, it's really that outcome variable that we're looking at. So here's a research question that we might, that may necessitate the need to utilize an independent t-test, assuming that our assumptions are in place. So on average, will male dieters lose more weight over a 3-month period than female dieters? Okay, so we have our grouping variable, it's dichotomous and nominal. We have male and females, okay? So there we have two groups and they're independent of one another. Characteristic of interest, our outcome, our dependent variable, is really weight loss. We're looking at weight loss in pounds over a 3-month period. Okay. So independent t-test compares the means of the two unrelated groups. Remember, it's the mean differences. It's parametric. Remember our definition for parameter. That also is derived within this idea of what a parametric and non-parametric test is. It's essentially used to report the means of each group and also the standard deviation. Is factored in. whereas a Mann-Whitney U, we also look at the distribution of values between two groups. No assumption about distribution, so it doesn't have to be normally distributed. And we're looking more at the median, okay, as opposed to the mean. And we can also look at the interquartile range, and that has to do with when you're looking at, best way to understand interquartile range is looking at the box and whisker plots, and they're portioned out into 4 different regions, hence quartile, and you can look at the values within that box and whisker plot. Okay, so we have a question. The variable height in inches is a clear example of which of the following types of variable. We have grouping, independent, dependent, characteristic of interest. I really don't like D. They use that term, but it is this characteristic of interest. Variable height in inches, interval or ratio. It could be either dependent variable or independent. Lovely to say it that way, but it can essentially be used as both. And if we used it as a grouping variable height in inches, of course it's not going to be dichotomous, so we can make some kind of dichotomous division. So for example, we can take all individuals who are over 6 feet and then all individuals who are 5 feet 11 and shorter, and then you have 2 groups. Okay, so it's artificial division. And that would be done based on some type of theoretical tenets, not just because you chose to do it that way. Okay, so we'll talk a little bit about how to compute this independent t-test. We're going to go through this these steps. What they do later is do some kind of hand calculations. Keep in mind that t-tests are run and often run and almost always run using your SPSS software. Sometimes people choose to use Excel program to run some of these statistics, and that's also possible as well. So now we're integrating some things that we had learned earlier in some of our lectures, like hypothesis, null hypothesis, and alternate hypothesis. So pull those from your database of understanding and apply it here so you can get a greater understanding here. So let's just say we're going to illustrate this test with data that come from a study of 17 male and 15 female dieters. So we have those 2 groups. And we're going to test the following null to see whether we accept it or reject it. Essentially, we're going to say that the null, as we always did, is no difference in weight loss between the male and female dieters. So we're going to go collect data, okay, run our statistical test, and then determine whether or not we accept or reject this, okay? And then it really stems from the research question, do male dieters lose more weight on average than do female dieters, okay? Based on this research question, based on the data who we have, it necessitates the use and application for running this t-test. Always understand that the research question drives the statistical analyses. So in this case, we're going to state the null, as we already did. There's no difference in weight loss between the male and female dieters. And then we'll state our alternative, which is not always necessary, okay? But for the sake of this example, we'll state it here. There will be a significant difference in weight loss between male dieters and female dieters. Now we're saying it's non-directional. So remember, if this alternate hypothesis was directional, okay, then we would say something to the effect of males will have greater weight loss than females. So we'd say it in one direction or the other. But in this case, we're just saying there's going to be significant differences, statistically speaking, okay? Not practically speaking, and I'll talk about that in a little bit. It's important to understand the difference. So we're just saying statistically that the differences that we observe between male dieters and female dieters, whatever we observe, we are assuming that the differences did not occur by chance, okay? So if we go through this manual approach to running the t-test, and like I said, typically you'll do this within your SPSS software, and you can integrate the significance level. We're going to define our probability as 0.05. So we would accept 95% under the normal curve and assume 5% for error. So it gives us a little bit more leniency as opposed to looking at 99%, then it'd be a little bit more strict. So we can look at the critical value. There's a t-table in your book. Again, if you use SPSS, it factors all this in automatically for you, but for the sake of understanding, it's good to look at it this way. So the table of critical values, we find that the critical value that define the rejection region are 2.042 plus or minus. So essentially, once we run our analysis and our statistic is greater than 2.042 or negative, or smaller than negative 2.042, then we're going to reject the null. Remember, if we reject the null, then we are saying that there are differences, because remember, the null says there are no differences. Okay. So again, preliminary analysis, we got to ensure that the data meet all our assumptions. One, that our grouping variable is dichotomous. We have the males and females. Okay, we're going to understand that it is from an independent random sample. All right, that's a methodological approach to collecting the data. That doesn't have anything to do with statistics at this point. Weight loss data are normally distributed, and the way to do this is we can look at the stem and leaf plot, and we'll show an example of that on the next slide. And the weight loss data are ratio measurements, so it ultimately falls under continuous. And here's our normal distribution. To determine, we look at this stem and leaf plot to validate that our assumptions are met. Okay, so here are just some of our basic descriptive statistics for the women and men. If we look at the differences, women, the average weight loss over 3 months was 12 pounds. Men was 18 pounds, 18 and a half pounds roughly. And the standard deviation is also important. It was about 5 pounds. One standard deviation above or below the mean for women, and the same for men. At this point, your eyes are probably getting a little bit large, and as are mine. This mathematical algebraic equation here is not really necessary if you're going to hand compute a t-test, because like I said, the SPSS functions take care of all this for you. Okay. Now, this is not beyond anyone's capability to hand calculate this, but of course, once you start getting to upper or more sophisticated analyses, some of these hand calculations are just really not feasible. But just understanding that the general nuts and bolts and the math that undergird these analyses, it's kind of good to see. Okay. So based on our findings, the computed t-test statistic is 3.16, so that's, remember, it's larger than our critical value. So we conclude that the difference in mean weight loss between males and females is statistically significant. Okay, so let's write it in a way that, you know, someone could see or understand in a report. We might say men lost an average of 18 pounds, okay, and women lost on an average of 12 pounds. This is a statistically significant difference at the 0.5 level, okay, based on the results of the t-test. Now, the differences that we found are statistically significant. This is important for you to understand. We found that these differences did not occur by chance, okay? The term significant does not imply magnitude or size, okay? We're not inferring that the difference between 18 and 12 pounds is large, okay? Now, there's a couple ways to interpret these findings now that we know that they didn't happen by chance. Okay, our test told us that these results did not happen by chance. In other words, if we went and collected data again and again and again, that we would roughly find the same results. Okay, that's basically what it's saying. But to now move to what we would term practical significance, there's two ways of looking at this. Maybe someone who understands the concept of weight loss, or a dietitian who understands the importance of the difference between 12 and 18 pounds is rather large, or the magnitude is great, then they can make that distinction in terms of practical significance. The other way to determine practical significance is to look at the effect size, and the effect size will then determine whether or not the magnitude of the differences is large. Okay. Now keep in mind this idea of statistical significance. The term significant in everyday language, in layman's terms, usually indicates magnitude, okay, or how large the differences are. But in statistics, the term significance carries a different meaning. So in this case, the word significant means that these results did not happen by chance. It's not inferring that the difference between 18 and 12 is large, okay? It's not saying that at all. The only way to determine that the difference between 18 and 12 is large. So there we have it, our two categories. Immunized versus those who are not immunized. And that wraps up the end of this presentation for Chapter 5.